Hello, Amir. Hello, Abdus. Hello, everyone. Today, we are making a brief tutorial for our video channel regarding how to fit sigmoidal data using MATLAB's curve fitting toolbox. This is a demo as well as a little bit of practice. And my name is Dr. Karche. I'm thankfully supported by Amir Parvaresh and Abdul Samad Mohammed. And in contrast to what it says as a date, today is the 31st of, never mind 31st, today is the 1st of November. And it's 1 o'clock, 1:30 p.m. today. And so our aim to explicitly sort of state our aim is to fit sigmoidal functions to data obtained from the literature, and the data that both Amir and Abdus have obtained from the literature is very specific. It is related to the voltage gated L-type calcium channel, and this channel's steady state of activation and inactivation gates. Okay, so ion channels have gates, and these gates have steady states of either activation or inactivation. We have now obtained data for these steady states, and today we're going to find out how to fit these data to sigmoidal functions using MATLAB. And the purpose of doing this fitting is explained in the green box at the bottom, is that these fitted functions will be used either in existing smooth muscle cell mathematical models by Abdus, or in mouse cardiomyocyte models by Amir, to study either hypertension or Timothy syndrome. And that is and to progress to that stage, for the next few days or so, we have to be processing our data in terms of fitting it to sigmoidal functions. And so to start, this slide illustrates what a sigmoidal function looks like. And it is strongly advised that you practice what the sigmoidal function should look like. Apologies, I'm still working on, yeah, okay. We should all practice what the sigmoidal function looks like. The graphs of activation curves and inactivation curves are drawn on the right-hand side. Activation curves usually are low for small values of voltage and have values of 1 as voltage increases. The graph for inactivation, steady state of inactivation, starts at values of 1 when voltage is small and goes towards 0 as voltage increases. Regardless, these steady states of activation and inactivation are summarized in the formula of function as written in the top left-hand corner of the slide. Just to read out this function, it reads as 1, which is divided by a large formula, and the large formula is 1 plus exponential of a minus sign that operates on v minus v half divided by k. So the exponential takes a large argument, namely minus v half divided by k. Regardless of activation or inactivation fitting, you will always do your fits to this function. The aim of fitting will be to uncover the values of v half and k. Incidentally, this function is called the Boltzmann equation. And by fitting your data, we are looking for values of v half and k. It's explained a little bit more on this slide here. In that, again, I've left the function, the sigmoidal function that we will use for fitting at the top, which is 1 over 1 plus exponential of minus v half divided by k. And in general, the properties of an ion channel steady states are enlisted in the yellow box on the left-hand side and illustrated in the graph on the right-hand side. The fitting must always be performed using the above sigmoidal equation. What I mean by above sigmoidal equation is that never mind that you always have v and minus v half, never mind it's always divided by k, but the exponential must always be minus v half divided by k. And so you must always fit all your data activation and inactivation steady states to this sigmoidal equation. Now, your clamped voltages, unlike in the example that I will show, are often between minus 100 and 100 millivolts, and therefore this is the range that you may wish to pick. Now, since steady states of both activation and inactivation are probabilities of an ion channel either being open or closed, the probabilities, the values on your y-axis must always be 0 to 1. If the values on your y-axis are between 0 and 100, then you must use something called normalization and make your y-axis between 0 and 1. The next piece of information that we must bear in mind is that when we are working out the voltage of half activation, its definition is shown in the red lines on the graph on the right-hand side. So I'll move my pictures elsewhere. And the voltage of half activation is defined as when the activation curve, so I'll point to it using a laser pointer, when the activation curve, which is the red curve, reads 0.5 on the y-axis, and you are then to take whatever voltage it is on the x-axis, and that is your voltage of half activation for this particular graph. Okay, a similar definition applies for voltage of half inactivation, in that you should follow the graph of the voltage of inactivation, and wherever the graph reads 0.5 on the y-axis, the corresponding voltage is the voltage of half inactivation. So this is one of the two parameters for each graph that we are looking to uncover using your data. And the final property in entry number E is regarding slope factors represented by K, either Ka for the slope factor of activation or K in A, slope factor of inactivation, and that the slope factors, the properties that you should realize is that in case of the red graph here, in case of activation, you can see that the slope factor here, the slope of this line here, is always positive. So you expect for the slope factor in case of steady state of activation to be always positive. Correspondingly, in case of the inactivation curve, your slope factor K in A is always negative, simply because the red line is, as you go from left to right, is increasing, while the purple line, the inactivation curve, is always reducing. And for that reason, once again, the slope factor for the activation steady state is always positive. The slope factor for the inactivation steady state is always negative. Now you have to process this in conjunction with our decision that we will always fit our function to exactly this form. So the minus sign must always be there. It must always be v minus v half. But when your Ka is positive, you're okay. But when your Ka is negative, your answer will turn out that the K has a negative value upon fitting. Okay, and that's what entry number E is trying to tell you here. So these are the properties. So please do process all of these properties. I know that this is not something that you fellas may be wanting to do for a living, but this is how biophysics goes. So these are some of the relevant properties of steady states of activation and inactivation. Moving on, before we go to the stepwise requirements, let's find out, before we go to the step-by-step fitting of data, let's sort of explicitly write down what we need when we're doing our fitting. When you do your fitting, you need your digitized data. Now, never mind that you need your digitized data, you have to know by reading the journal article, by processing for yourselves, that the digitized data is actually for steady states of gates and not for the corresponding time constants. We are not at the time constant stage yet. Okay, we will get there, but we have to finish with the steady states of activation and inactivation as illustrated on the right-hand side. So the digitized data is something that you're looking for. You are also looking for MATLAB with the curve fitting toolbox in it. And that should be open in your computer simultaneously to this digitized data. The plotting scripts that you may have made, something that I may have shared with you. And finally, I wish that you have either electronic or paper notebooks where to write down your answers, because it may be, I hope, that we have at least 5 or 10 data sets to fit. And so this will be a sufficiently sort of high value information that you want to write down in some sort of secure place. And so these are the requirements. But so and so as a policy, as a lab policy, I propose that you organize your data in the following manner. In that you firstly make individual folders, and in said folders you put the article, you copy the article, you not move the article from your main PDF repository to there. Rather, you copy it to that folder. You give this folder an understandable name. Okay. And in the same folder, you must put the digitized data. In today's case, it's the steady states of activation or inactivation. And in this manner, you can also put copies of your MATLAB programs in there, whatever it is that you need used for processing. And in this way, we can then, between you and me, we can share individual folders, if not all folders together. And your data then becomes that much more organized and systematic. I'll now take a pause and take any questions you may have before we proceed. So both Amir and Abdus are going to do their own presentations in a minute. So let's proceed to the next slide, which is step number 1. And step number 1 is just to get your data file, ASCII data file in order. And I've literally copied and pasted my example data file in the pink box towards the bottom left-hand corner of the slide, where the first column, as highlighted by my pointer here, represents some sort of voltage. So although my voltage may be make-believe, and just for example, the voltages that Amir and Abdus have will be from actual data. In my example's case, I have 2 more columns. So my second column represents my inactivation data from some hypothetical experiment. And my third column represents data for a hypothetical activation data that I got from somewhere. And upon fitting, I expect my first column and second column to give me the purple line. some sort of inactivation, and I expect my first column and my third column to give me the red line as shown on the right-hand side. Is it clear enough, Amir? Is it clear enough, Abdus? Thanks. In step number 2, and this is something that we will do momentarily after I finish running through the slides, you are essentially looking to load your data into MATLAB, not into the curve fitting toolbox, but simply into MATLAB. And you might import your data into MATLAB using the command prompt, using these 3 or 4 lines of simple code. And once you have loaded your data into MATLAB, you should then start the curve fitting toolbox from the apps menu at the top. Okay, and that was step number 2, summary of step number 2. Step number 3 is that once you've started your curve fitting toolbox from the apps menu, you should assign values to X data by picking X data from the relevant pull-down menu. So to assign values to an object called X data, you pick the X data from the relevant pull-down menu. In a similar manner, to assign values to an object called Y data, you pick something called Y data enact from the pull-down menu. We will see how this works in a minute. Okay, we will see how this works in a minute. And so once you have assigned values to both objects X data and Y data, there is a panel somewhere in the middle of your curve fitting toolbox where you should choose custom equation. And in this custom equation, you should write exactly the formula that I'm indicating with my laser pointer here. You must then uncheck autofit, and you must then click on fit options. And in fit options, when you are fitting in activation data, you can take lower values of k as -10 and upper values of k as -0.01. You can take lower values of k as -100. As discussed in slides before, as long as k is taken to be negative, that should be fine. Okay. So all these instructions may or may not be marginally customized for inactivation fitting. And again, in the fit options, you should also assign low and high upper values to V-half as something between 0 and 40. The reason I pick 0 and 40 is because my voltage runs between something slightly more than 0 and something slightly less than 40. So you read whatever voltage you have here, and you read whatever voltage you have . Could you not hear me at all?
Just for like 2 seconds, 3 seconds.
You could not hear me for 2 or 3 seconds.
Yeah, at the end.
Okay, so
at the end.
we can then continue. We can just continue. I have no idea what happened. And so the way I choose my minimum and maximum values of voltage is by looking in my data file. In this specific example of the data file, the minimum is somewhere close to 0, and the max is somewhere close to 40. So that's how I chose it. That is my motivation for choosing these lower and upper values. After that, you press on close and then you press on fit. And all being well, the curve fitting toolbox will give you values for V-half and K, which you should then proceed to write down in your notebook. But fine, that is exactly what step 4 is. is that you write down these values so that you do not forget. And for example, when I did the fitting last time, and hopefully it will come back to the same or similar values in a minute, I found that the V-half of inactivation of my example data set was around about 18.2 millivolts. And that my slope factor is firstly negative. It carries a minus sign. And its value is minus 1.9 millivolts. Notice, fellas, that V half and K both have units of millivolts. Okay, and you should always use those units. And the final step is that you repeat steps 1 to 4 for all data sets, including activation and inactivation. Okay. And so someone is going to help me with slide number 12 momentarily. And so Abdus, unless you say otherwise, I propose that we now proceed to the actual demo of how we might fit a sigmoidal to this example data file. Should we do that?
Yeah, sure.
Can you see my screen now? I'm not showing the slideshow, but I do have the slide open in front of me.
Mm-hmm.
Okay, so step number 1 is to make sure that you have your data file in an organized manner. And so over here, tell me if you cannot see the data file, Amir. I'm showing you my data file, and I'll highlight the 3 columns of data that I have. The first column is my pretend voltage. My second column is my example inactivation. And my third column is my example activation. Reason you need to know what's in which column is because that is how you will access your X data and Y data in MATLAB, as well as in the curve fitting toolbox. You do not have to have 3 columns in a data file. As long as you have 2 columns, you will be able to fit the data. Okay. But for what it's worth, I have 3 columns, and I will be fitting an inactivation curve to the first and second columns of this data file. That's fine. And so having gone through step 1, step 2 is about loading the data into MATLAB. And so the first line says that we will use a variable name called AP data raw on the left-hand side of the equal to sign. And into that, we will load the data called amirdata.txt. Now, if we go to MATLAB, you can see on my left-hand side current folder, there is a data file called amirdata.txt. And if I paste the line, pardon me, Microsoft PowerPoint changes how I write single quotes. You can see that AP data raw is now uploaded or imported into MATLAB, as you can see on the screen over here. This matrix is now imported into MATLAB. And the next thing to do is assign values to X data, to assign values to Y data in ACT. And let's just do that because Y data ACT is an exercise that both Abdus and Amir are quite capable of doing. So I'll copy this. And I will paste this again in MATLAB in the hope that it works. And it did work. And so there is now a matrix called X data due to this thing that I wrote here. So in X data, I put the first column of my AP data raw. And so I have voltages here, 6, 9 till 30. And in a similar manner, I have Y data in ACT object where I again have the inactivation data uploaded. which started in my example data file called amirdata.txt. But fine. So having done my step 2, I will proceed to doing step 3 now. Using the mouse, start the curve fitting toolbox from the apps menu is what slide number 9 says. And if I go to my apps menu, I have a button over here that says curve fitting, and that's the curve fitting toolbox. And if I press on that, a little graphical user interface comes up like so in front of me over here. And the next sort of piece of information is that to assign data to an object called xData, pick xData from the pull-down menu. For assigning data to an object called ydata, pick ydata enact from the pull-down menu. So I'm going to go and do these 2 lines first using my mouse key. And so somewhere towards the top left, I see that I have xData over here. And there is a pull-down menu where it says none. And so if I see, I have an xData object there. So that is what I choose. This xData object appears because I've done these 2 or 3 lines over here. Okay? Okay. Fellas, do not become concerned. We will do this together as often as is necessary. And similarly, you apply the ydata enact to the ydata. Yeah. We then proceed to find out what the next instruction is about how to write the custom equation. And you have to choose custom equation and write that formula there. So I will try my luck. I'll copy this formula and see if I can do that in MATLAB. So here, where it says polynomial, I will change this to custom equation. So you're not looking for the inbuilt fitting functions, but you are going to give MATLAB a custom equation. So you choose custom equation. And you can see that it already comes with some sort of custom equation. And you may be able to write a custom equation here. And so as you can see, your fit is nowhere close to your data. The data are shown by these small circles here, and the fit is shown by this horizontal line over here. And for that reason, we have to first uncheck the auto fit. So let's go and uncheck auto fit. So there's an auto fit option over here on the left hand side, on the right hand side, pardon me. And you have to uncheck the auto fit. Followed by, you have to assign lower and higher values to K and VHAF in advanced options, in fit options. There's a section called fit options where you're supposed to assign low and high values of both K and VHAF. Let's try to do that. So here I have my fit options. You can see the fit options here. And if I press on that, I have a whole bunch of stuff that comes up here. Yeah. And I may have forgotten, but my favorite algorithm is the Levenberg-Marquardt algorithm. So I wish you use that. And you also make it by square. You also make it by square. You don't have to. You do not have to. You can just follow what is written in the slides. Okay. But what is important is that the lower value of K, because this is inactivation, should be given -10 or something suitably small. And the upper value should still be negative, but it should be somewhere close to 0. And the VHAF, in my case, the lower value is 0 and the high value is 40, because that's the range of my data. That's how far my data goes. I do not have a voltage lower than 0 and higher than 40. Okay. And so I've now given bounds to both my parameters K and VHAF. Okay. In the expectation that this may or may not work better. Okay. And so with that, I will go and find out if there's any more instructions here. It says press on close and press on fit. So here's the close button. So you press on close. And apparently there's supposed to be a fit button here somewhere. Can someone point out where the
underneath auto fit?
Right.
On
Where does that
the right
happen?
side. On the right side.
On the right side.
Top right.
Top right. Okay. So
Yep.
here's the fit button. Okay. So I'm supposed to press on fit over here. And if I fit, you can see that you have your data as circles, filled circles, and the line represents your fitted sigmoid. As you can see, the sigmoid will work only when your y-axis is between 0 and 1 and never for any other ranges. Okay? You will have to change your custom equation for that. And the next thing, the important thing to do now is that you have to take pen and paper and make note of this v-half and k that you found. So in my previous test, I found v-half to be 18.3 and k to be minus 1.9. I wonder what I found now. So my v-half is about 18.67. It really does not matter whether it is 0.67 or 0.69 or 0.5. As long as you've got the 18 point something, you are in the ballpark. Okay, you're really close. Okay, and furthermore, because I have barely 1, 2, 3, 4, 5, 6, 7, 8, 9 points, every time I fit with a different range of k, it will give me a different k value. What is most significant here is the minus sign. You must have a negative slope for your inactivation. And as long as this minus 1.558 is really different between control and Timothy syndrome, between control and hypertension, your math models are going to show the phenotype of hypertension and Timothy syndrome. Okay, and so at this place, I choose to write these two numbers on a piece of paper. Yeah. And proceed with my customized plotting programs. So when I close the curve fitting toolbox, it asks me, do I want to save this session? And I don't want to save this session. You may wish to do otherwise. Okay, but what I do, the next instruction being do your fitting for everything else. What I do after I have finished fitting is the following, in that I write a small customized script which may then help me superimpose my experimental data onto my fit and make a nice graph, legible graph, which I can put in my thesis, in my research articles, whatever. Let's try our luck here. Let's see if this might work or not. And so there you have it. And so I make understandable annotated graphs where I show my data generally as glyphs. And I made both your graphs purple because our presentation was using purple for inactivation. Yeah, so I kept the purple color. So you can color code your graphs. You make your font size big enough. You have tick labels, as many as you need, but not too many. You don't want 50 tick labels between 0 and 1. The relevant tick labels are the minimum, where v-half happens. Where v-half happens, yeah, and certain other features. Okay, so this is a picture. So you can go File, Save as PNG, and that's a picture you can literally put in your thesis. Okay. Now, before I stop sharing, fellas, I'll take questions. since we have all of this in front of us. Okay, so so it looks like we're just about okay. So Amir, could you do us a favor and read through slides 7 till 11 for us, please, slowly, so that everyone catches what you're saying, please.
On the following slide, what you can see is the data that has been loaded from the digitized folder. You can see 3 columns. The first one is showing the voltage, the second one is showing the inactivation, and the third one is showing the activation. Using the voltage and using the inactivation, you will obtain the purple inactivation line. Using the voltage and the activation, you will obtain the red line. That's showing the activation, and this is showing the K, the V half, which takes place at 0.5. Moving on to the next slide, this is what will be utilized to obtain the fitted sigmoidal. On the left-hand side, before the equal sign, a name will be given to the data. It will be loaded into MATLAB. Then the X data will be used. The 1 represents the X-axis. The X-axis is the inactivation values obtained from literature searches. For the Y data, the same process will be applied and the Y data will be obtained. The same will take place for activation. Moving on, using a mouse and the curve fitting toolbox, the X data will be pulled down and will be inputted into the curve fitting toolbox. The same will be done for the Y data. From the middle panel, the custom equation will be used, which is shown underneath. This will be copy pasted into the curve fitting toolbox for the sigmoidal shape to be obtained. Auto fit has to be turned off, and the fit option will be clicked. In the fit options, values have to be assigned to K between the ranges that have been obtained. The same has to be applied for V half. The upper range is the highest value of voltage obtained, and the lowest is 0. Finally, fit will be clicked, and a sigmoidal will be obtained. The V half value and the K values will be written down in a notebook or an electronic format. The data will be saved in the same folder that the articles and the digitized images will be placed into. This process will be repeated for activation using the exact same formula, just that instead of using the inactivation, the column 2, the third column will be utilized, which is the activation data.
Thank you, Amir. Well done. Well done. Abdus, whilst Amir broadcasts slide number 12, could you explain to us what our lab's policy and plan are, please?
Yeah, sure. So in order to stay organized, our lab's policy is that we save our work in our computer's project folder and not on the cloud, because we do not trust the cloud storages. We ensure we take notes and write our names and dates anywhere that we can. And next time we will plot the data and fits together to generate results. Then we will remodel the SMC and the cardiomyocytes.
Thank you, Abdus. Thank you, Amir. Everyone can stop sharing now. I'll take questions before we stop recording. Is there any discussion that you would like to add to this recording, Amir?
No.
Abdus, is there anything you'd like to add to this recording?
No, everything was clear for me.
Thank you for participating, and we will continue the conversation after we stop recording.